Okay, so today we're going to look at more sorting, question 3, which sort. So we're given the question that web developers have many different types of sorts that they can use in their toolbox, and they're saying, like, for these scenarios, which sort should we use, like, provide the best sorting algorithm, and in addition, also state the worst case runtime. Okay, and we're given like some nice options. So we're given merge sort as one option. We're given quick sort with whore partitioning. There's also the red, white, blue quick sort, but that's not what they're talking about here. We're given insertion sort, and we're given LSD. And LSD is least significant digit sort. So here in part A, we're told that a list of n packets are received by a server over time, and each packet has the timestamp. So it already has the timestamp which we're sorting by. Like, to sort, we need something to compare by. And we're being told that the timestamp is what we're comparing by. And we're also told that some packets may be dropped, or they might arrive out of order due to the faulty network. So so even though we expect it to be like sent in the correct order, some stuff might be dropped, and some which means like they're going all the way to the end. Some of them might be a bit out of order, like maybe like there's a race, like two of them happen at the same exact time, and like we count one slightly faster or something because there was like a lot of build up. Who knows? For some reason we're told that like they arrived out of order due to this faulty network, and we're told to sort this list by the timestamp. So since let's go through all of these. So for like merge sort, and quick sort and LSD sort, something we're not really like looking at is the fact that like most of it is probably sorted already. So whenever you hear that most of the list is probably sorted already, you want to say insertion sort. And with inversions, like we could specify like the runtime. But what's really important here to note is that like there's no point in like spending a lot of time sorting if you already know something about your data. If you know something about your list that it's already mostly sorted, there's no point in like spending the time to sort. And that's why insertion sort would be the best here. And we're also asked to give like the worst case runtime. The worst case runtime for insertion sort is of course O of n squared. So O of n squared. And to give this in terms of inversions, like the general formula is this is the worst case, but the general formula for insertion sort is going to be big O of n plus k, where k is the amount of inversions you have. Generally, the worst case is when you have the amount of inversions k you have is n times n minus 1 over 2. And obviously then your runtime will be big O of n plus n something of order n squared, which is just going to be big O of n squared. So hopefully that helps show it to you. I guess like to expand upon like this bit a bit more, like you could say big O of n plus n time n minus 1 over 2 is in here, because this factor is on order n squared. And then this thing is kind of like negligible asymptotically. Just doesn't make much of a difference. Okay, on to part B. So now we're given a list of n websites, and each website has the number of total visitors, and we want to sort by the visitor count. So let's think about our data. Here we have the number of total visitors. So what do we know about the number of total visitors? Well, there's not much we can say off the bat. Like that sounds like pretty random. It sounds like pretty uniformly distributed. And whenever you have like uniformly distributed, quicksort is never really like a bad choice. We also like don't in terms of like stability, like you don't explicitly need stability here, so there's really no need to use merge sort. In terms of like insertion sort, you could have like a lot of inversions here, so that wouldn't be the best, as you wouldn't want n squared runtime. And for LSD sort, that could work, but that requires you to know like some upper bound on the number of visitors. So if you knew some upper bound on like the number of people that can visit a website, then maybe LSD sort can work. But quicksort is really the answer that we're looking for here, because the reason why LSD sort really doesn't work is we don't know upper bound. And like quicksort does work because it is like random, like uniformly random data, and we have no need for stability. So okay, part C, after sorting by visitor count, we now want to sort by web page file size. So now here it's saying after sorting, so that gives us like some indication that we want stability. Like this implies stability. And if they have the same file size, then they are ordered by visitor count. Like, so since we want stability, let's look at our other stable sources out of the above. Merge sort is a good choice. It's stable. It's the fastest stable sort. So I guess for now we could just put merge sort down, but just because it's stable. Let's look at the others, like quicksort. The 3-scan like red, white, blue partitioning version is stable, but like here we're using Hoare partitioning, which is not stable. So we cannot say that it's stable. So let's look at insertion sort. Is insertion sort stable? Well, insertion sort is not stable, so insertion sort also wouldn't work for part C. And finally, LSD sort. LSD sort is stable, but we don't, once again, we have the same problem. We don't know an upper bound, right? So it's like the same issue. Even though LSD sort is stable, we have the same issue, so we can't say that. Okay. And then finally, for part D, we have a list of 20 names. So here we'll notice that our list is actually of a very small size. Like 20, like n equals 20 is like a very small size. So generally, when you want to like sort like something of a small size, insertion sort is a good way to go. Because of small size. Like 20 is relatively small, like compared to like asymptotic stuff where like if you're looking at like Google data centers, it's like hundreds of thousands or like millions or billions of items in a list. Like compared to that, like 20 is really small. For LSD sort, that wouldn't really work here. We don't know like anything about the names. Are all the names like a million digits long, or are all of the names like 10 digits long at the max? We can't really say. And we would have to do like some like padding with LSD sort. So well no, we wouldn't. We would have to do that with MSD sort. My bad, I misread this. This is LSD sort. So yeah, but we don't really know that. For quicksort and merge sort, insertion sort would be faster because of the small size. So for here, even if there were like order of n squared, like 20 squared is still a constant, so we could upper bound this by like of like 400, which is like O of 1. Even though this is all asymptotically, this is still O of 1 because we have a constant size, like a small constant size that we're given. So hopefully this helps you out with like realizing when to use which sort, and catch in the next one.